So we start the exercises next. And let's see this one first. Here we have to find dy dx. Y is given as a function of this variable u, y equals 2u cube, and u itself is a function of x, 8x minus 1. So you can understand that we have to use the chain rule here to find dy dx. So we start the solution accordingly. By the chain rule, we have this. Dy dx equals dy du times du dx. Now y is 2u cube and u is 8x minus 1. I have skipped some steps. You can understand what those steps are. First of all, by the constant multiple rule for differentiation, this 2 will come outside, and then you will have ddu of u cube, which by the power rule would be 3u square. 3 comes down, and then in the exponent it gets reduced by 1, so it becomes 2. And that 2 and that 3, they get multiplied and they give you 6. So that way you get 6u square. What happens here? First you apply the difference rule. ddx of 8x minus 1 is ddx of 8x minus ddx of 1. ddx of 1 is 0 and ddx of 8x by the constant multiple rule is 8 times ddx of x, and ddx of x by the power rule is 1. So that's why you get 8 from this entire part, and 6 times 8 is 48. So that way the derivative is 48u square. Next we have number 4. In this one, y equals cos u, cosine of u, and where u equals this function of x, minus x divided by 3. So in the solution, I am not again and again going to write by the chain rule we have. You can write those parts. So we straight away just simply write what the chain rule is. dy dx equals dy du times du dx. Here y is cos u and u is minus x divided by 3. The derivative of cos u with respect to u is minus sin u. Always remember that whenever you have a trigonometric function and you want to calculate its derivative, if it starts with co, there will be a minus sign. Okay, you just remember that. And what about this? Here, first of all, minus 1 divided by 3 comes out by the constant multiple rule, leaving you with ddx of x, which is 1. So that's why this part only is minus 1 divided by 3. So that way your derivative is 1/3 of sin u. Whatever problems we do not solve here, you can try them out yourself. Okay, so, and if you do not get something, or you find some problem very difficult to solve, you write in the comment section below. In this next set of problems, this is what we have to do. In the following exercises, write the function in the form y equals f of u and u equals g of x. So we have to do this split ourselves. Then find dy dx as a function of x. And let's take this one, the 10th one, y equals the 9th power of 4 minus 3x. So you can see that y is just a function of x. So we have to now cleverly split it into these two parts using whatever f and g we can, so that we can apply the chain rule nicely. So obviously we can split this function into two parts like this. We can imagine y as the 9th power of u, where u is 4 minus 3x. And then of course we apply our usual chain rule. So here you have to write, now by the chain rule we have all those things. So dy dx equals dy du times du dx. Y is u to the power 9 and u is 4 minus 3x. The derivative of u to the power 9 with respect to u by the power rule is 9 times u to the power 8. And differentiating this using our usual rules, you get minus 3, because 4 contributes 0 to the derivative, and by the constant multiple rule, minus 3 comes outside and ddx of x is 1. So that way you get 9 times minus 3 minus 27 u to the power 8. But do not leave the answer like this, because you introduced this variable u. Okay, it was not originally given in the question. So that's why you have to write what u is finally and have the answer like this: minus 27 times 4 minus 3x to the power 8. And in fact, it was mentioned also in this part, in this set of problems, that you have to not only find dy dx but express it as a function of x, not as a function of some other variable that you have defined. Next, let us take the 16th one. Here y equals cot pi minus 1 divided by x. So in this case also the split is obvious. You can write y as the cotangent of u, a new variable where u is pi minus 1 divided by x, so that their composite is the given function. And then we apply our usual chain rule: dy dx equals dy du times du dx. Now y is cot u and u is pi minus 1 over x. I ran out of space here, so I put the multiplication dot here. If you want, you can put your usual cross also to make it more prominent. But anyway, so what is the derivative of cot of u with respect to u? Minus cosecant square u. Again, you see, this is a trigonometric function which starts with co, so there will be a minus in the derivative. After that, whatever comes. And what do we get from here? Pi of course gives you 0 when differentiated, minus ddx of 1 divided by x. Now we already know from our previous study of derivatives that the derivative of 1 divided by x with respect to x is minus 1 divided by x square. Or you can also apply the power rule with negative exponents. 1 over x means x to the power minus 1, so that minus 1 comes first. So you have a minus here, and then minus 1 gets reduced by 1 means you have x to the power minus 2, which when you write as a fraction it looks like this. So that means ultimately this is your derivative, minus cosecant square u divided by x square. But keep in mind, you have to write what u is. So we need to write one more line. So this is the final answer: minus 1 divided by x square times cosecant square of u, that means cosecant square of pi minus 1 divided by x. Next, we have another one involving trigonometric functions. Y equals 5 times cos to the power minus 4x, or you can also write it like this: y equals 5 divided by cos to the power 4x. So in this case also the split is obvious. You can write y as this function of u, 5 times u to the power minus 4, where u is cos x. And then by our chain rule, dy dx equals dy du times du dx. So here y is 5 u to the power minus 4 and u is cos x. So I did two steps here at once. First, 5 went out by the constant multiple rule, and then by the power rule, the derivative of u to the power minus 4 with respect to u is minus 4 times u to the power minus 4 minus 1. That means minus 5. And the derivative of cos x with respect to x, of course, is minus sin x. And then after some manipulation, you can see that this minus and minus, they will give you plus. 5 times 4 is 20 u to the power minus 5 times sin x. And then you write what your u is. U is cos x, so that way you get the derivative as 20 times cos to the power minus 5x times sin x. In this next few problems, we have to find the derivative of the given function. Say this number 20. So here, whether you want to split the function like that into two parts or not, that is up to you. You can either do that and apply the chain rule, or you can straight away apply the chain rule to this itself using the outside inside rule, if you remember. So what I am going to do for this one, I am going to solve it, that is find the derivative in both the ways. Okay, and then we will slowly leave this splitting. We will start doing it directly. So we first adopt the method of splitting. We have seen 2 or 3. So let's first do it that way. Note that the given function q is square root of u, where u is equal to 2r minus r squared. Let me draw your attention to one more thing. Note that the dependent variable here is q, not y, and the independent variable is r, not x. The authors did it deliberately so that we may get confused. If we have got used to having y as the dependent variable and x as the independent variable too much, then that will be a problem for us only. That is why sometimes you will see that other names have been used for variables. So that is why here actually the derivative is dq dr, not dy dx. Y and x are not there. And accordingly we have to write the statement of our chain rule also carefully. dq dr equals dq du times du dr. And also one more thing, it's not necessary that you have to name this new variable u only all the time. You can name it anything you like as per your convenience. But anyway, let's come to the actual thing now. So what is q? Q is square root of u. So ddu of root u times ddr of 2r minus r squared. Now you already know what this derivative is. We calculated it way back. 1 divided by 2 times square root of u. And here of course 2 will come out of the differentiation process by the constant multiple rule. ddr of r is 1 and minus ddr of r squared by the power rule is 2r. And then there you can cancel 2 from the numerator and denominator, giving you 1 minus r divided by square root of u. But remembering that we have to write what u is, so we write 2r minus r square under the radical sign. So this is your derivative of q with respect to r, but using this technique. And now we are going to see an alternate solution where we won't do these things. We will straight away do the calculation. Let us see how that goes. So in this alternate solution, we straight away write we have dq dr equals this, ddr of this, what q actually is. And now your outside inside rule, that thing comes into play. So differentiating this function means you are entering that house. You recall that analogy. So this square root is your first room. Entering it means differentiating the function, leaving the inside intact, not changing the inside. So the inside room remains the same in this whole process of entering the first room. And you already know what is the result of you entering the first room. 1 divided by 2 times square root of the inner room. 1 divided by 2 times square root of the inner room. So you get this times, and then you are entering the inner room to do whatever you want. So that's why times ddx of, oh see, I myself made that mistake. See how easily we get used to things. It is not ddx, it is ddr. ddr of this. So you see that you of course know what is going to happen next, and we are eventually going to get that. But I am going to write things however. But before we do that, you see that this method is very fast, and actually you have to learn to differentiate like this itself without doing those splits. I mean, actually you are doing split in your mind, but you are not writing the details. So let's now write and see whether we get this itself or not. So in the next step, of course, this part will remain the same, and ddr of 2r minus r square as before is 2 minus 2r. So you note that this is multiplied with this. So you can cancel 2 from numerator and denominator here also. And after you do that, this is what you get, identical thing. We should get identical thing. Next, let us consider this 22nd one. Here, the dependent variable is s and the independent variable is t. S equals sine of 3 pi t divided by 2 plus cosine of 3 pi t divided by 2. Because we have already seen applications of derivatives in some simple problems in mechanics, that is calculating velocities and accelerations of moving bodies along a straight line, of course. And in those applications, we used the letter S to denote displacement and T to denote time. So it looks like the displacement of some moving object as a function of time. And because sine and cos are appearing, it looks like it's a simple harmonic motion. I'm just simply saying, okay, it looks like that. So in that sense, we are calculating the velocity of the moving object if we are differentiating. But anyway, let's leave those physical applications and come back to mathematics. So here we have ds dt. So ds dt means first what will you do? You apply the sum rule for derivatives. So that way you get ddt of sine of 3 pi t divided by 2 plus ddt of cos of 3 pi t divided by 2. So here immediately you did not have to apply the chain rule in its inside inside form. But now in the next step you have to do that, because here you have got two rooms. This outer room is sine and the inner room is this 3 pi t divided by 2. So first you differentiate the outer room keeping the inner room intact. That way you get cos 3 pi t divided by 2, and then you multiply that with the derivative of the inner room 3 pi t divided by 2. The same happens with this term also. Differentiating the outer room, which now is cos, you get minus sine. Again, do not forget, co means a minus will come. Cosine, cotangent, cosecant, derivatives of all these things come with a minus in front. So minus sine 3 pi t divided by 2, again with this one also, times the derivative of the inner room with respect to t. Alright, now what are the derivatives of this inner room? Because you have t, by the constant multiple rule, 3 pi divided by 2 comes out. And then ddt of t is 1, so that way you get 3 pi divided by 2 with both the terms, which you can take common out. And that way, this is how you get your derivative. 3 pi over 2 times cosine of 3 pi t divided by 2 minus sine 3 pi t divided by 2. Next, let us consider this number 38. This one is going to be a little cumbersome. Here q equals cot of sine t divided by t. Here the solution immediately uses the chain rule in its outside inside form. So here the dependent variable is q and independent variable is t. So the derivative is dq dt. So first you differentiate the outer room keeping the inner room intact. Because you have cot, you get minus cosecant square of sine t divided by t, and then you multiply that with the derivative of the inner room. I said it would be a little cumbersome because of this. You have to apply the quotient rule here, no other option. So then this part continues to be the same, and here we have applied the quotient rule. So the denominator gets squared, and in the numerator first you write the denominator as it is, that is t, multiply it with the derivative of the numerator minus the numerator times the derivative of the denominator. So derivative of sine t with respect to t is cos t, and derivative of t with respect to t is 1. So this is your derivative, minus cosecant square of sine t divided by t times t cos t minus sine t divided by t square. And I don't think you can do anything more to simplify this, except you can do one thing. you can bring this minus over here and make this sin t minus t cos t. Oh, and one more thing, do not think of cancelling sine and cosecant, okay? This is not product, this is sin t is inside the function cosecant square, or cosecant, we can think of it that way, square is there outside. So it's the input of cosecant. That does not give you 1, I mean you cannot do any cancellation here. Next, let us take this number 48. This one is interesting because here you have y equal to 4 sine of square root of 1 plus root t. It is interesting, maybe you have already seen why it is interesting. Here there is one outer room, then inside you have another room, and inside that you have another room, maybe a closet. So you start your differentiation using the outside inside form of the chain rule and write dy dt. So your outer room 4 of course will first of all go outside by the constant multiple rule, need not think about it. So first you differentiate the outer room, you get cos. The entire inner room and the room within itself, everything remains intact, untouched. So square root of 1 plus root t. Then you multiply that with the derivative of the inner room. And here itself you have to apply the chain rule once more because there is another little inner room sitting inside. So this part remains the same times. Now when you differentiate this thing, the inner room, there also there is a square root outer room whose derivative is 1 divided by 2 times it, that you already know. That also you have to multiply now with the derivative of this inner room. Actually I was trying to say that this is the inner room, but this entirety is the inner room of course. 1 plus root t. Now we did a little cancellation here, 4 divided by 2 is 2, and we have clapped these things together like this, cos root 1 plus root t divided by root 1 plus root t. And what is this? 1 gives you 0 and derivative of root t is 1 divided by 2 root t. So now the differentiation process has stopped. I mean you have gone to the innermost room and there is nowhere else to go. So now what are we getting from this? So in the next step, after cancelling this 2 and this 2, this is how you get the answer. Cosine of this divided by this times square root of 2, and that multiplication happens in the denominator. Next, let us consider this 52nd one. Here we have to find the second derivative of y with respect to what is the independent variable is x, and y is 9 times tangent of x divided by 3. So that means we have to differentiate it first once and then we have to differentiate once more that derivative. So we start by calculating the first derivative. If you are using Newton's notation, that is y prime, that is you are not showing the independent variable, that is okay, but keep in mind that it is x. So what will you do to differentiate this? Again we have to use the chain rule with its outside inside form. So 9 anyway is outside everything and the first room is 10. So you have to first differentiate this keeping the inner rooms intact. In this case there is only one inner room. So tan gives you secant square when differentiated, secant square of x divided by 3 times the derivative of the inner room. Instead of again writing ddx of x divided by 3, I have straight away written the derivative. You can also do things like this, skipping steps, once you get good at it, but be careful to not make any mistakes. And whenever you do something, please recheck what you have done at least once. So then after cancelling this 3, I mean there is a cancellation, This is how you get the derivative. 3 times secant square x divided by 3. But of course, the job is not over yet. We have to find the second derivative. That means we have to now differentiate this again. So then we go for the second derivative, y double prime. Now, what is it about y double prime? Y double prime is not exactly like this. Although here also you have to apply the chain rule. Note carefully that here there are 2 rooms, a nested sequence of 2 rooms. The outside room is the tangent room, the inside room is x divided by 3. Here actually there is a nested sequence of 3 rooms. The outermost room is the square room, inside of which you have the second room, and inside of that you have the x divided by 3 room. So accordingly, here the calculation will be like what we did there. But I have done it at once, and eventually you will also be able to do at once. See, what exactly are we going to do if we differentiate this using the chain rule with its outside-inside realization? 3 of course stays outside. First you will differentiate the square room, keeping everything else inside intact. So differentiating the square room means what? 2 comes down. 2 has come down. The rest stays as such, because derivative of x square is 2x. So this is that x part. Besides this 2, this is that x part, secant x divided by 3. So you have conquered the outermost room, and this part stays like this. I am denoting the 3 derivatives, or rather I am emphasizing the 3 derivatives separately by using these square brackets. You have differentiated once the outermost room and you have got this. Now I am going to differentiate the next inner room, that is the secant room, keeping the innermost room intact. The derivative of secant theta with respect to theta is secant theta times tan theta. Or if that sounds weird, derivative of secant x with respect to x is secant x times tan x. So secant innermost room times tan innermost room. This is the other derivative. And then we have to differentiate the innermost room also. And when you do that, you get 1 divided by 3, because ddx of x is 1. So this way, you can apply your chain rule as many times as you want to go to break your way inside a complicated expression like this and get the job done in 1 or 2 lines. But again, let me caution you, you should do this only after practicing these things a lot, that you have gained confidence and you know that if you do things like this, skipping steps, you won't really make mistakes. Then only you should do it. But first you have to really, in a rather boring way, go through all the steps carefully. And as you gain experience, you yourself will start skipping things. So that is the second derivative of this function with respect to x, of course. Now there are many problems that I have left out, simply because there are many. So I urge you to do those things and see how it feels, whether you are really getting the answers that are available in the end of the book or not. Whatever mistakes you are making or not making, so you see those things carefully, and whatever you need, you just write in the comment section below. And I am stopping the video here itself. There are of course many other exercises. I think 2 or 3 more videos I will need to complete this set of exercises completely. So see you in the next calculus video, whenever that is. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.